Here is a wave on a string. The waves are traveling to the right, and we can see that the waves keep on forming. We're not just making one wave. This type of wave that continues to be produced is called a continuous wave or a periodic wave. By contrast, I could also send through just one wave, like this, a perfect wave shape. This is called a wave pulse. A wave pulse is when you send just one through, like this. And it doesn't have to be an entire wave cycle. A pulse could be just the top of a wave, or it could be just the bottom of a wave. So there are lots of ways to create pulses. This is also a pulse involving two crests. We can distinguish these by drawing just a single pulse like so, traveling along the string, or if we want, we could draw a second type of pulse wave like this. By contrast, a continuous wave is one that just keeps going like this. And it keeps on traveling to the right. A pulse wave is a wave that does not repeat. A continuous wave is a wave that repeats. And we also sometimes call these periodic waves. There's a second way to distinguish types of waves besides periodic and pulse. So far, all of the waves we have seen look like this. The wave is traveling to the right, moving this way, and the particles are oscillating up and down. So the direction of energy transfer and the direction of particle oscillation are perpendicular. But what if we produce a wave on a slinky like this? So we're going to push the slinky coils in and see what happens. Which way are the particles or the coils oscillating? Are the coils oscillating up and down, perpendicular to the energy transfer? No. This time, the coils are oscillating left and right, and energy is transferred to the right. So in this case, we say the oscillation of particles is parallel to the direction of energy transfer. That contrasts with the first type we saw, where the coils or particles oscillate perpendicular to the direction of energy transfer. So here, the particles, the coils, are oscillating up and down, which is at a right angle to the rightward energy transfer. To capture this second distinction, we use the words transverse and longitudinal. First, transverse waves are the kinds that we make on strings. So first, let's draw a string with no wave. By contrast, longitudinal waves are the kind that we make on a slinky or a spring. So here is a slinky or a spring with no wave. Okay, so what does a pulse transverse wave look like? Something like this. How do we know? Because the particles have oscillated this way, and the energy transfer is this way. So we could define a transverse wave as a wave in which particles oscillate perpendicular to the direction of energy transfer. And we see that because the purple and the red are at right angles. Let's now draw a longitudinal pulse. Here's the medium, and then in the middle you've got this compression. And then on the other sides there is nothing, no compression, no stretching. But the other way that you could draw a longitudinal wave, a pulse, is like this. Instead of having a peak, you could have a valley. Over here, instead of having a compression, you could have a stretched region. And that stretched part will travel through the medium. Longitudinal waves are defined. Each is a wave in which particles oscillate parallel to the direction of energy transfer. Here's a real slinky, and we're going to show a slow-mo video of a compression traveling through. This is a single compression pulse traveling from one end to the next. And you can see it kind of bounces back, but it loses energy. That energy loss is what we call damping, and it can happen in longitudinal waves too. It's possible to create not just a single compression pulse. The same way that we can produce a continuous up-down wave, we can also produce continuous longitudinal waves. So let's watch. We're going to actually have lots of compressions. They will repeat. And you can see the compressions traveling across. Here they go, all the way across the medium. The compressions are one type of region. The other thing you see on this slinky are expanded or stretched out regions. The expansions are called rarefactions, and there's a rarefaction between every two compressions. So if we pause the video, here's a compression because it's darker, here's another compression because it's darker, and this spread out area in between is called a rarefaction. Let's record that in our notes. Longitudinal waves are made up of compressions and rarefactions. The word is not, there's not an R right here. It's not rarefraction, it's rarefaction. When we look back to a transverse wave, we see there aren't compressions and rarefactions. Instead, the analog is crests and troughs. Another way to think about these are peaks and valleys, but the phrasing that we'll use are crests and troughs. So let's go back up here and take a moment to draw a continuous transverse and a continuous longitudinal wave. The continuous wave looks like this. You have crest, trough, crest, trough. Those crests and troughs repeat. Over here, what is repeating? Compressions and rarefactions are what repeat. So you have compression, rarefaction, compression, rarefaction, compression, rarefaction. This is a continuous longitudinal wave. If we come back down, compressions are regions where there's high or low density and pressure. Answer that question. Which one is it for compressions? Is it high density, high pressure, or low? And then likewise for rarefactions, what is it? High or low? You can talk with your neighbor, fill this out, and then move to the next page.